Okay, today let's do something a bit different. We're gonna implement a proof for a game, the game of Sudoku. So the game of Sudoku is the rules are pretty simple. You have a grid that is 9 by 9, and you have to fill it with the numbers 1 to 9, the integers 1 to 9. Some of them are going to be given to you. That's the puzzle. But you have to fill with some simple rules. Every row has to have the digits 1 to 9 once and only once. Same for columns and same for sectors. So it's you can play online. There are puzzles that are simple and some of them are very, very hard. So this is an example. So this is a sector. And other than that, you also have obviously rows and columns. All right. And our proof is gonna say that you know a solution, but you don't want to reveal it. So your solution has to be valid according to the rules of the game, and also obviously has to match the input the puzzle numbers, the given digits. All right. So how do we do that? Okay. So let's start with putting the skeleton. Sudoku.rs. I'll put it to low as bean source. And I have to add it to this guy, pub mode Sudoku. Then I'm going to do the skeleton code, which is usually a circuit. So Sudoku circuit. And it has, okay, so it's going to be pubfn test Sudoku, and it result with nothing or error. An error is this plonk error. So this part is essentially the boilerplate. You can skip it. I usually do that. But it's pretty mechanical actually. Okay, and then mock, and then you want to run that. Some size, and then you need a circuit. You need an instance. So at the beginning, it's going to be instance pre-empty. Then that returns the prover. And the idea is that the prover can be verified. So something like that. The circuit will be something from Sudoku. And we expect this guy to have the solution. So I'll call it solution. And the solution is what's our grid. But usually I prefer not to have two-dimensional stuff, even though it has rows and columns, because indexing is very annoying, in my opinion. So I essentially put everything in the row. So instead of having 9 by 9, it's 81 in a row. It's pretty easy to go from one to the other. So that's just going to become a vector of values of FP. And the value is this guy. And FP is the palace dude. Okay. So we need a solution. All right, so let me generate a solution with our friend ChatGPT. ChatGPT. I think we can do that. Hopefully. Give me an example of a Sudoku solution. Okay, that's pretty good. And I want it to be in a single line. Put it as a list of 81 number digits. Okay, so same thing. Oh. I would like it comma separated. Okay, so that's good. Copy code. And then we have our solution. Okay, and only thing we need to do is convert the solution into a solution that has values of FP. So I need to map this into, so it's a value, it's a known value, and it's a FP from the integer. Then I collect, and that becomes the solution here. Okay. So circuit, continuing the boilerplate, circuit has to implement the circuit trait on FP for Sudoku circuit. And usually that means that we also need a config. Struct config. And that guy has the columns. What I do know, it has the clone. And this guy needs to have default. Default. Okay, so circuit has yeah, prompt, that sounds good. Can generate now the boilerplate config would be Sudoku circuit config. Floor planner is a simple floor planner. Without witness is a self default. And now we have configure and synthesize. All right, so configure is how we lay out our circuit. So since we have to work with blocks of 9 digits, because we have to verify that there's blocks that have exactly the digits 1 to 9, not repeated, it seems natural to have 9 advice columns. So I'm going to do let advices be 0 to 9 and map that into meta advice columns. Then I collect into a vector. Then I can enable the equality thing, the equality equality support. So that would be a clone. And for instance, okay, I could have the same thing. I could also have 9 instance columns, but really, you want to have your grid, your operating system grid, your set of equations, as small as possible. And usually you have a lot of rows. So if you add a column, then you're going to add a lot of cells. And so it seems to be usually preferable to have fewer advice columns and spread the input data on several rows. So what I'm going to do is only have one, the primary instance column, dot instance column, and I have 81 rows with the problem, the puzzle input. The other thing is that you can't have a program that has a variable number of rows. So even if our puzzle is going to have different numbers of given digits. So for the digits that are not given to us, I'm going to put a 0 inside so that the size is the same and the offsets are all predictable. So primary is that's how to do meta enable on equality on primary. And I don't think we need any constant here. That's it. So usually after that, so we also need to have a chip. Okay, so we have a chip, Sudoku chip, and this is where we implement our logical gates. This guy has a config, which is the Sudoku chip config. Let's call it chip config. And that guy, we don't have it yet, so let me have it as a struct as well. And so we know this guy has the advice column, and we know we now have 9 of them. So let me put this guy as a constant of an array of size 9. And we have the primary column for the instance. These guys will be put into our chip config import column. We want the prong one, and we need advice, and we need instance. Okay. All right. Then typically this guy has to derive from clone and debug. And this guy has to derive from clone or default. I forgot actually. Clone for sure. All right. And so we are saying that Sudoku chip implements the chip trait. Chip. And let me see how this expands. Chip. Then that we bind this to the Sudoku chip config. This guy is nowhere, no state to load. This guy returns cell chip config. We have just Sudoku chip, so this one is config only. Okay, and this one has done. All right, and then usually what we have is an implementation that has 2 methods. One method is construct, with essentially you take of configuration. So you take this guy, and you return a chip. The way you do that is pretty simple. You just put the config inside. The second one is the interesting one, is the configure, where this time you are giving you're giving this stuff here the same thing as the configuration here. So you are given this guy. Let me remove this and import it. It's pretty long. Okay, we are giving this here, and we're also given the columns. That's the most important thing. We have the advices, which are the same types of this stuff, so I might as well copy them. I hate when this stuff happens. All right, so we have advices, and we have our primary. And what we do after configuration is to return a new configuration. So this guy. And here, this is also where we are setting up the whole thing. So at this moment, I don't have much here. Just that I'm gonna have to copy the primary, this guy. So this is just a skeleton at the moment, so we don't have a logic yet. What else is missing here? Synthesize is to do, but that's expected. All right, so why do we have errors? Okay, so this is one error. It's probably because I don't return anything. Okay, I expect to return something. All right, so once we have that, we create the chip config. And chip config, I know that it's a Sudoku chip based on the configure. I'm going to be given meta and the advices columns and the primary. So as we said earlier, and the chip config would come here. Okay, so why is it error? This one doesn't have the chip config. Chip config, and we know it's a Sudoku chip config. All right, and one error here, because advices is a vector and we are passing it as an array. All right, let's do the try into unwrap. Okay, so one error left. FP is not known. Really, that's the problem? That's an interesting problem. Could that be the problem? FP from integer. Yeah. Mhm. Okay. I should be. Oh, and yes. That's not the problem. The problem is this difference here. I have to do a star. Okay. All right. So we have our solution, but we should also have a problem. All right. So solution without a problem is not very useful. So let's create a problem. I will put it like this, and this is going to be the puzzle. And the puzzle is essentially the same thing as the solution, but we are going to blank out some of the values so randomly. Normally, of course, supposedly the Sudoku problem has only one solution. Therefore, I can't have just that. Or maybe this one is very, very simple. Anyway, it doesn't matter. We're not here to actually solve the puzzle. We just care about how our solution matches the puzzle. And as instance, we don't want value. We want the actual FP. So need to remove that. And now I have to say that it's a vector of FP. Okay, and I put that as a puzzle, as an instance. So what we have here is that on the one and only instance column, I'm going to have these 81 numbers. I don't do anything with it yet. So let's see how this runs. So I have to run this guy and test. Oh, let me just put test here, and I think that should work, Okay, this error. Failure. Instance too large. That means that this 4 is too small. We want 81 rows because we have the instance and 81 rows of that. So what's the closest power of 2 is 128, so I need 87. Okay, fail. What's going on here? Failure, this is cool. What's the problem? Oh, there's error here. Not yet implemented. That's this part here. So I'm just going to do OK. All right, so we pass this. So this is so far just loading the puzzle. We haven't done anything with the solution. Well, the solution is inside the circuit, but it's not loaded inside this object circuit, but it's not actually loaded on the proving system grid. All right, so we have to do that. Okay, so let's do that. Let's do that here. How do we load that? So we have to load row by row because we have constraints. Right? So the constraint we have that the numbers have to be 1 to 9. Let me put them as gates because they will have to be implemented as gates. So where are they? The Sudoku configure. So we have to be 1 to 9. It has to be unique. And it has to be, so it has to equal the, when it's not 0 in a given cell, it has to be equal to the puzzle. And finally, it has to be no dupes. Right. Okay, so actually there are 3 rules. So that means we have three gates. So 3 gates means 3 selectors. So I'm gonna create 1 selector for the puzzle. that's a selector. One selector for the range. So it's puzzle first, range, just a meta selector, and finally no dupes. So SD is no dupes. Selector. Okay, and these three guys are going to end up in the config. So I might as well put them here as well. So this was what? SP, SRSD. SP, SRSD. Okay, port. And clearly I need them here as well. SPSRSD. Okay. All right. And then we have the equality stuff is done over there. When we construct, we have done equality. We have advice columns. Okay, so now we have just to put the gates. All right. So the first gate, create gate, is the gate that is saying that we are equaling our puzzle. So this is normally a equal of the instance, but here's a bit difficult because the values are not always going to be equal. If the puzzle value is 0, we want to have anything match that particular value in the instance. So it's only when the instance value is done 0 that it has to be equal. So that's a custom constraint. Meta here. So, but that shouldn't be too hard to do. Okay, so we grab the selector, query selector on SP, and we have to grab our. Okay, so this has to be true for every advice. So this is gonna return 9 constraints, one for each column, because we have one full row. So the idea is that we're gonna have one row for of digits for the our puzzle, and just below one row of instance, and then one row of a second row, and then second row of puzzle, third row of the solution, and third row of the puzzle. So we're gonna lay out that like that to check that part, and then we are gonna recopy the solution, but then in column, and then in sections. Right, and so we activate different constraints for these rows, but the first one would have all the constraints, would have to have SP, SR, and SD, and then the ones that check the columns and the sectors, we only need to have the check on the digits not repeating, because we have already checked that the digits of the solution match the digits of the given digits, and we also have matched that the solution digits are from 1 to 9, so we don't have to repeat that test when we are checking the columns and when checking the sections. All right, so for this one, it's gonna be a loop. Okay, so we need to have these constraints already. It's this way, and then we have to loop from 0 to 9, because we have nine columns. 9 columns mean 9 constraints. And the constraint would be that, okay, if we pick the value of the advice as being meta query advice, at column what? Column advices of I, and on the current row, right? This is one guy, and then the next row is our puzzle solution. So this same thing, but on the next row. Next row, we want A equal B, or B equal 0, because B is the B is the puzzle. If B equals 0, we are free to put whatever we want. But if B is not 0, then B has to be equal to A. All right, so how do we do this? So A equal B means A minus B equals 0. And B equals 0 means B equals 0. So if we multiply these two guys, we have the expression that fulfills this condition. All right, so what's going on here? Let's constrain with that. Okay. So usually we have to put a clone. Okay, let me put it this way. But I think we need a clone. And these constraints have to be pushed into string. Okay. And then we return them. So we return them by saying constraints with selector SP, and these are our constraints. All right, so as expected, B, we don't like it because it's not clonable, it's not copyable. We have to clone it if we use it twice. This is our first constraint, that if we activate SP, we need to check that the row and the next row are matching unless it's a 0. Okay, so we can try this one first. But to try this particular constraint, I have to lay out the first row of our circuit. So let's do that, because currently our circuit is empty. So I go with the layouter. I say I'm assigning a region. The region would be let's say first 2 rows, and the assignment is where I put the data on the first 2 rows. So we can do that as we have to do that as a loop, because we also have 9 stuff. And then on the region, we assign advice. So this is, I don't know, we can say this is solution. On the column, this is the config dot chip config dot advices I. And then, okay, so this is going to get boring very soon. So let me extract this guy. And this is going to be chip config. Chip config advice. The offset is 0 because it's on the first row, and we assign it to our self and solution of I. So this is actually the first row, but we have to repeat that. We have to repeat that 9 times. All right, so this has to loop through as well. First 2 rows. So this is actually columns here, right? For J, and I denote that as column using the J index. Solution J. Okay, and then the instance guy. So the instance guy would be assign advice to the puzzle, same column, but now offset 1. And I can't copy from advice because this is not actually coming from advice, it's coming from the instance. So it's assign advice from instance, different signature. Signature is okay, instance. So this should be chip config primary. Only have 1 column. And then the offset, right? The row. So that row is okay, so might as well do the loop actually here, because we have to repeat that for every row anyways. So let's do this properly. And then this way we already have the logic for the 9 rows. So expect that. Okay, good to do here. Oh, what's going on? No, I think constant primary. Then the value would be the row in the primary is I times 9 plus j, because we multiply the row by 9 and we add the column. That's how we go from the 2D and to 1D. Advices would be that's correct. And then offset is 1, and then that's going to be the something is too long here. Okay, where is the signature? Oh, we have 5. Yeah, we have only 5. I don't know how we have 6. That's why there's a problem. This guy is useless. And then we do the tycoon. All right, so this copies the instance into the proper position on the second row. And that's it. We have to activate the condition we have, the sector we have. So meta, it's not meta. So it should be chip config dot. This is the primary check enable one on the row on this region and on row 0. Then it matches 0 and 1. Okay, layouter has to be mutable. Like this. And then I don't need the OK, and I don't need the to do anymore. It should be OK. And this guy should be good. Okay. First, okay, so this is a good bad name. Copy solution to grid. All right. So we are copying a solution to the grid with the puzzle given digits, and we're checking that they match. Okay, let's try. Oh, we failed. And what's the error? Sudoku constraint not satisfied. So that means that either, well, we have to have made an error with our constraint. Okay, so what error could it be? Two types of errors. We could have placed the stuff in the wrong page, in the wrong location. So let's check that first. And it seems like that has to be the case because solution here is only j, and we're not using I. So I forgot to multiply I by 9 plus j here to place the proper solution. And then this guy here is row at the end. That should be good. Let's retry this then. All right, that's good now. That was the only bug. Okay, so that's number 1. Number 2 now. Number 2 is about. Okay, so we did this one. Number 2 is about that the digits have to be between 1 and 9. Okay, so we create another gate. Create gate. The name, I would say, is 1 to 9. And the constraint. Okay, so what are the constraints? So the constraints usually are equality constraints. And the one that I have here is more like a inequality because I want them to be between 1 and 9. And the stuff is not very good for that. It's actually quite terrible for doing equality constraints, inequality constraints, or range constraints. But luckily, we have a helper guy for. We have a helper class for that in the UDPs of gadgets. And that's called a range check. If the expression is not super long, I mean, the range here is not very large, then this is okay because basically what it's going to do is if you say that it has to be between 0 and 9, it's going to do c times c minus 1 times c minus 2, and so on and so forth. So if the number of of the range is relatively small, well, it has to be small, then this is okay. But if it's a large range, obviously this is a polynomial of degree n. Not very good. All right, so the way we do this is the same. We grab the selector, and the case here is that the selector is digits, so it's SD. All right, this code is D, right? No, SR, SR for range, SR, and SR. We also want to do the same loop because this has to also be valid for every column. So it has to be something like that. But this time we don't need to do on 2 rows, just 1 row. And the constraint is that A is in the range 1 to 9. So the range is actually starting from 0. So that's going to be 0 to 8, but the last number is exclusive. So it's 0 to 9, but 9 is excluded. And A here is it is 1 too high, so I have to minus 1. It's A minus expression constant FP1. That's A minus 1. What's going on? Oh, just import. Okay, so if I do a range check on this returns me an expression. And that is my constraint. Okay. Seems to be okay, that's to be good. Something wrong? Oh, I have to do the return, of course. So I'm returning this with the sector range. Okay, so now that we have that, we can enable this constraint on the first row as well. So on this first row here, we are going to enable SR as well. So this means that if our solution has, for example, 16 here and 16 here, this should fail. Actually, first let's try without. Let's try normally and see that it succeeds. Okay, now let's see what happens if we put something that is not equal. That should error. Yeah, that errored. So we are saying has to be the same. And now let's check the range. Is it 40? So it's still equal, but it's out of the range. Where's the equal here? About this. And we fail as well. Right? So we have briefly tested the 2 constraints already. So we are only 1 more to go, which is the fact that the digits have to be all different. Yeah, if they're all different and they have to be between 1 and 9, it means that obviously they have to be 1 to 9. Okay, so that's the last stuff. I'm also gonna copy paste this guy. This one a bit tricky because if you want to check whether digits are from 1 to 9 and any permutation, with this constraint of arithmetic constraints, you can't really check that by sorting or anything because that's too complicated for just the arithmetic formula. But in this particular case, we are kind of lucky because it's we know it's going to be exactly 1 to 9. So we can use the commutative property of addition and multiplication to make sure that if we sum all these numbers, we are going to get the same result. And if we do the multiplication of all these numbers, we're going to get the same result. We cannot just do the sum, because if we do the sum, you can have duplicates by offsetting one number, incrementing one number, and decrementing another number. So instead of having 1 to 9, you could have, for example, 2, 2, and then 2, 2, and then instead of having 3, 4, you have 4, 4, right? Something like that. Yeah, because you decrement 2, 2, you decrement 3 to 2, and then you have to increment 1 to more, so 5, 5. So 1 to 2, 5, 5, 6, 7, 8, 9. And that should be the same sum. So the sum is going to be same 45, which is 1 to 9. But we also want to be the product to be the product of 1 to 9. This way, if both match, then it has to be the numbers 1 to 9. Okay, so let's do that. Now it's SD, and we're returning SD. All right, so for this, what we have is we can use the fact that these expressions we can do 0 to 9, then fold them. Fold. The first value is expression constant. For addition, the starting point would be 0, and then the function that combines them is what? What's going on here? Thought. Fold initialization constant. All right. So we have to do A times B. No, A times, we grab the column expression, this guy, and multiply by it. This is B, and this is the index. So that's the index here. And then we do A times 8 plus B. And then the result will be should be 45. So this is the sum. Yeah. But we want the sum to be 0. So we could do sum minus 45, or we can actually do the trick of starting at minus 45. That means do from 45 negative. So now the sum should be 0. And then for the product, we have to start from 1. And I don't think there's a trick for that. We start from 1, and then we do 8 times B. And this is the product. So product, it's we expect that to be constant if E from, it's 9 factorial. Let me see what is 9 factorial. What is 9 factorial? Factorial 9. This one. Okay. So we want that guy to be this value here. Okay. And the constraints are actually only these two constraints. We have the sum and the product constraints. Okay, something's going on. Okay, we don't need that guy, that's why. This time is not a constraint per column, it's a global constraint over all the columns. All right, so we also need to activate this dude now on this first row. And now okay, if that works, we can do that on the columns and on the sections. Let's see, gonna be interesting. Well, actually worked. It actually worked. So if it works, it means that, for example, if I do 4 and 4, this will match to the two constraints I had before, right? The puzzle and the solution match on that particular number. The numbers are between 1 and 9, but now we have duplicates, so this should error. Yeah, and that errors. Okay, so that's pretty good so far. So now we have to do the column and the sections. So to do columns and sections, I actually need to store the regions that have been assigned to my solution. So this guy here, when I say I put the value into a cell, I kind of want to know what cell it was. So this function here should return a signed cell. So let's call it cell. And in this guy, I would have an array of cells. And then add the cells to this guy. Okay. And now I can return the cells here instead of doing OK of cells. So I'll return the cells. That makes them available here. Okay. And then I need the grid. Right? And the grid is going to be the same story. It's a mutable vector of assigned cells. So then I have to append them to here. I extend the stuff with the cells. So that puts all my solution cells into this grid variable, so that I can now do the copy of this. So kind of transpose and put the columns down per row to check them, because my constraint is my gate that checks the constraints is working row by row. All right, so I have to do J. So I'm going to loop through columns and then rows. J into to keep the fact that I is a row and J is a column. I do it like that. Okay. All right, so I have loaded the stuff. What I would like to have is a helper function that takes 9 advised cells, 9 cells, and then puts that into a row and checks that. Okay, so that's why we had chips actually. Otherwise, so far we use everything as a circuit. So this is the config. I should have the chip somewhere. Oh, where is the chip? Chip is here. Okay, here. Implement the chip. I have the configure. I also want to have the check row. This takes self. This takes the meta. This guy, the layouter. Sorry, the layouter. And then it takes the row, right? So the row is a signed cell and FPFP, and we have 9 of them. And that's it, I think. And that should return nothing, because all I'm interested in is putting the constraint in there. All right. So if I have that, what do? I do layouter dot assign region. The name is check online. Okay, check no dupes. And the assignment is on the region. And now what do we do with that? We do for for I cell in row dot terrible iterated and then enumerated. So I get the index and the cell itself, and then I say that I want to copy that. So copy advice annotation or whatever. Don't really care. The region is the table region. The column what is the self dot config dot advices of I, and the offset is obviously 0. So copy advice and okay if I succeed. And now I have to enable the gate. So I do it by doing self.config dot D is no duplicate, right? Primary, region, range, and no duplicate. So I have to enable that one on that region, offset 0 on the current row. Okay. Now that I have to check row, it's I can use that. I can use that to here, right? So I need to get the to put take the column and put that into an array of 9 assigned cells. So actually the easiest way to do that is through the collect to. So our column is 0 to 9, and then we map that as our grid. Grid dot I times 9 plus j. Then this is going to be a assigned cell, so I just have to collect that guy into a vector of assigned cells. This is a problem, probably because it's here. Okay, so this is implied. Yeah, a vector of assigned cells. So once I have the column, I can use a check row, but I need a chip first. So my chip was Sudoku chip construct based on the chip config. Chip config. Config was given to me, right? Yeah, config is given to me. So it's config dot chip config, and now I can do chip dot check row, passing the layouter, which is over here, and I put a namespace to have no conflict. So it is color. And then we have the row of 9 assigned cells. So which is our column that I have to do the try into and wrap to cast from a vector into an array. All right, so that's it. All right, what's going on here? I have to clone this. All right. Okay, so this is going to check each column. Let's run this. Here should pass. And now the probably the hardest one is the section guy. It's really the same thing, but it's the now it's a question of how you do the math. So to do sections, we know what we have 9 sections. So the loop would be still from 0 to 9. So now it's section in 0 to 9. And then section is group of by 3 by 3. So we have ISEC, which is section divided by 3. and we have JSEC, which is sec modulo 3. This will repeat ISEC. Yeah, we cut basically sec by 3. And now we have in each section, we have also to loop like exactly like this guy, with J. And no, do we? Yeah, we do. No. We have just to do this guy here. So this is a section because the loop is inside the. This is the loop here, 0 to 9, and let's becomes like that. Do we have one too many? Okay. So this section is 0 to 9. I should have I. It's gonna be a bit more complicated than this. So what do I do? Inside a section, the index here has to be also cut in 3. So the I is index divided by 3, and J is index modulo 3. Modulo 3. Right? And the position in the grid now is the combination of ASEC and I. So the real position is for I is ASEC multiplied by 3 plus I, and JJ is JSEC multiplied by 3 plus J. And now the grid position is II plus JJ. I hope it didn't mess up. Yeah, because ISEC was going to be between 0 and 3, 0 and 3. It's a major, it's a minor, major, minor. I think it's good. This is section. This is section. Okay, so 9 sections, and each section we have 9 values. Okay, that's 40 bits. What do I have code here? This is a copy paste? Looks like a copy paste. Yeah, okay, I will use this one. Okay. All right, so this is the columns and this is the sections. Okay, so let's try. If that works, it's actually the end. Okay, run. Uh-oh. We're not using this stuff. This is very strange. 139. 139. Yeah, this is normal. I'm just creating 9 advanced columns, so the index doesn't matter. Okay, seems like this is it. Okay. Oh, why? Why? Because it's in the test. But then it complains. This guy's weird. Complains when I put it there, but it complains when I put it there. So I'm gonna remove it from here, and I'm gonna qualify it. Oh, it's because it's a test, so it compiles differently. It's fine. That's okay. I'm just gonna make it qualified there. All right, so no warning, and I think that's it. We have. All right, so we have a verifier, a Halo 2 verifier for the game of Sudoku. It's not completely fully tested. I assume that if you have a problem with the columns, it would check it. But it works with rows and works with rows, so I assume it's gonna work. If you find a bug, yeah, please fix it. But other than that, I think this should be correct. This one, it's working. And if I change anything here, it's gonna blow up. But I cannot put 0 in the solution. Yeah. It's okay to put 0 anywhere in the instance proposal. Yeah. Okay, that's it. All right, so how many lines? About 200 lines. Yeah, 200 lines plus the test. So the code is about 200 lines. Is there anything we could have done better? Probably could have made it a bit smaller because these guys don't have to be on separate lines, but other than that, it's pretty clear, I would say, what it does. So we have that. And yeah, I think I wouldn't change this code too much. I don't think there's any well, there's not much room for improvement. We have factored it pretty well. Yeah. Okay. So that's it. That is the Hello 2 circuit for the game of Sudoku. Next, I don't know what to do next. Maybe another game, or you let me know if you have suggestions. Otherwise, I would find something that is doable in about 200 lines. I think we have longer than that. It's going to get too boring or too difficult.